documentation is that I don't know where is the line. Yeah, over here, I think they start to pull into, let me go to the exact line first. Yeah, so over here, they try to run the circuit into their back-end machine, which unless you apply for a token through the 10 minutes free simulation, I don't want to go through that, but you can try to register an account to IBM Qiskit and then get the token for the 10-minute run per month. Unless you do that, you basically cannot run this particular code. So I rewrite parts of the codes so that it runs on the local computer through a simulator. So this code, later on, I will run this. And yesterday, I tried to document some of the changes that I can do. Unfortunately, I cannot implement everything yet. You see why, but I did make some implementation, some modifications to the codes. So I will also tell you how you can try to modify the codes from IBM Qiskit so that you can test to factor other numbers using Shor's algorithm. So I think we can go to Shor's algorithm for today. Okay, basically for Shor's algorithm, you have two, I would say you only need two, you only need to know two sort of like algorithms. And these two algorithms, they are sort of like the inverse of each other. So if you understand the first one, which is the Fourier transform, you can more or less understand the second one better. But here are some preliminary results that I think is better that you know. So the first thing is that you already know this. If let's say your psi is a vector, so you can identify the eigenvectors of some unitary matrices by equation 46. And because this is unitary, you can sort of like understand that the eigenvalues are given by just a phase. And this is the basis of what we want to do later on. We want to estimate this particular phase. That's the role of basically Shor's algorithm. So there's also some subroutines running inside. I think one of the subroutines I did not manage to complete the slides, so I will just tell you verbally, but you can look at it through the Qiskit documentation as well. Second thing is to understand how to write down the fraction in the binary form. So the decimal representation that we are used to is such that if let's say you have a decimal number, the decimal 1 here means that you multiply with 10 to the power minus 1. And then 5 here, the first 5, you multiply with 10 to the power minus 2, and so on and so forth. This is how we will represent decimal places using the decimal representation. So for quantum computers or like even classical computers, you can only represent it through the binary representation. So you need to convert everything into the binary form. Not every fractions you can convert precisely into the binary fraction because you need to know that sometimes like they just go into infinite loops because it's 2 to the power of minus 1, minus 2, and so on. So you need to pick a certain precision that you want to achieve using the binary fraction form. So in this case, if you perform the calculation, this is the exact representation of 0.15625, whereby this one here represents like you multiply with 2 to the power of minus 3, and then the next one you multiply with 2 to the power of minus 5. If you sum them up together, converting back to the decimal fraction, you find that this fraction is exactly the same as this one. Okay, so again, like I said, the binary fraction is only useful because we can encode it using qubits. So let's go into the factorization problem first, before we go into the algorithm. Let's say you have some equation. You have a dividend A, your divisor is M, your quotient is K, and you have a remainder B. So you can always write down the set of division equation by this equation. But in a more general terminology, you can use the congruence relations, which is written by this. So over here, B is not necessarily your remainder anymore. Any number that has the same remainder, you can write in this form. That's why we call this a congruence relation. For example, okay. So for example, what is 1 mod 15? 1 is 1, right? Because 1 cannot be So if you expand it into the first equation, 1 cannot be divided by 15, so the remainder is 1. So 1 mod 15 is 1. 2 mod 15 is 2. 4 mod 15 is 4. 8 mod 15, 8. 16 mod 15 is 1. 32, 2. 64, 4. Do you notice a pattern? So the first one is 1, second one is 2, and then 4, 8, 1, 2, 4, and so on. So it repeats by itself after a certain, what we call as the period or cycle. So there's a repetition of the outcome after every 4 numbers for this particular example. So this repetition is what we call as the cycle period. The length for this example is 4. Every four iterations, it repeats by itself. Okay. So over here, I said that 2 to the power of 4 is equals to 1 mod 15. And if you move the 1 to the left-hand side, so 2 to the power of 4 minus 1 equals to 0 mod 15. And when it is 0 mod 15, it means that your remainder is equal to 0. That also means that 2 to the power of 4 minus 1, you can, 15 can divide it perfectly, right? So then you can use the difference of squares, meaning that you separate out this 2 to the power of 4 minus 1 into 2 parts, a squared minus b squared. So you can separate out into a minus b, a plus b. So in this case, you just break 2 to the power of 4 minus 1 into 2 square minus 1 multiplied with 2 square plus 1. Okay, and we established the fact that 2 to the power of 4 minus 1 can be divided by 15, or 15 can be divided by that, depending on which number is bigger, right? So it means that 2 to the power of 2 minus 1 and 2 to the power of 2 plus 1, these two are the factors of 15 by itself, right? So then you sort of identify the factors for 15. And in this case, we call that prime factors. And this is the main sort of like key part of the RSA cryptographic system, whereby you try to find two prime numbers, multiply them together, and then you get a very big number. And the fact is that when you know these two numbers, you multiply them together, it's easy for you to find what is the result of your multiplication. Whereas if you know the very big number, but you don't know what is a prime number, it's very hard for you to find the prime numbers. So this is what we call as the one-way function, whereby it's easy for you to compute in a certain direction, but it's very difficult for you to compute in another direction. So in this case, finding the prime factors are very difficult to do. So Shaw's algorithm sort of like promise to be having a faster approach compared to the classical approach of finding your prime numbers, your prime factors, sorry. So if you want to generalize this type of formulations, then basically you can write something like this. For any number n, as long as you can find a to the power of r divided by 2 minus 1 and a to the power of r divided by 2 plus 1, you sort of identify the factors for n. So there is one caveat, because everything operates on integers. So it means that your r has to be even. Otherwise, you are doing square roots, and it is not an integer anymore. So that's why r has to be even. So roughly speaking, this is a sketch of finding the factors for a large number. So roughly speaking, what will be the procedure of factoring algorithm needs to do? So if let's say you have two prime numbers p and q, and you want to factor n, so the first thing that you need to do is to identify the greatest common divisor of a random number a with n. So the greatest common divisor has to be equals to 1, meaning that they have to be co-prime. Co-prime means, for instance, if you look at 15, so is 6 a co-prime of 15? What is the greatest common divisor of 6? 3. So it's not a co-prime. How about 2? What is the greatest common divisor of 2 and 15? It's 1, right? So 2 is co-prime with 15 because the greatest common divisor is 1. So what will be the other co-primes of 15? 2? Huh? No, 3 is a factor of 15. 7, 4, and then 8, and then 11, 13, 14. So these are the possible candidates for your guess for the first step. Okay. So the reason why you need to identify the greatest common divisor is that if let's say you manage to find a number with the GCD not equals to 1, like for instance 15. So let's say you identify 6 as your random number and the GCD is not equals to 1. Then it means that part of the factors, the prime factors of 6, is the factor of 15. So in that case, it's 3. Get it? So the first step is to identify your GCD. You need to make sure that the ones that you want to run the algorithm with, it has to be equals to 1. So that's the first requirement. So now if your GCD is equals to 1, then you try to find the period of the period R of this number. So if this is odd, then you need to go back to step 1 and select a different A. Because remember that when R is odd, basically this equation 47 doesn't work. In order for equation 47 to work, your R has to be even. Is it okay? So this is a second requirement. So once you know that your R is even, then you formulated this particular equation, right? So you minus 1 on both sides, and then perform this step. Perform the difference of square. Then you manage to identify um, your prime factors up to a certain common factor k. So roughly speaking, these are the steps of a factoring algorithm. First, randomly pick a number, identify the GCD. If the GCD is not equals to 1, you need to select again. If the GCD is equals to 1, then you proceed to the next step. See whether or not your period is equals to is a even number. If it is even number, then you manage to factor it by minus 1 on both sides and then do the difference of square. If it is a odd period, then you go back to uh, step 1, select another random number. So it's like going through a loop, trying to search for some number that satisfies uh, the two conditions, the GCD equals to 1 and your period has to be even. Then you slowly sift through your solutions. For a very small number, you probably won't see the significance. But for a very big number, then you see the difference. But for this introduction, you just go through like 15. So this is okay, right? Okay, so the next thing we want to introduce first is what we call as quantum Fourier transform. Um, for non-physicists or non-scientists, basically, I don't want to go into like what is a Fourier transform. The short answer is you can try to rewrite a certain representation, let's say from the time representation to the frequency representation and vice versa. But if you don't want to go into that definition, you can think of it as a unitary matrix that acts on a certain states, and it gives you equation 48. Okay, so the capital N over here is just 2 to the power of small n. So let's look at one example. Try to write down this particular unitary matrix. Oh, okay. So this is a given equation. Sorry, let me zoom in. So this is a given equation. So I substituted n equals to 4. Basically, this is equals to 2 to the power of n. So the sorry, the example that I mentioned is that the small n equals to 2. So the capital N will be equals to 4. So this is 1 over square root uh, n. So it's 1 over square root 4. And then the jk equals to 0 to 3. And then the capital N, you just substitute to 4. And then this is the equation. So one thing that you can see is that because your phase, I already defined it for you to be e to the power of 2 pi I over 4. So when your omega is to the power of 4, basically it means that it is e to the power of 2 pi I, which is equals to 1. So far here is okay. So now the second step, what I did is to change the index to run from 0 to 3 so that it runs from 1 to 4. The reason why is because it's easier for you to identify what is this element. So let's look at one example. What is this thing? This will be 1, 0. Okay, because it's 4-element thing, so it will be 1, 0, 0, 0, 1, 0, 0, 0. Right? So this is okay. Another thing, because I already changed the index, so it becomes 1. I move the 0 to 1 so that you run from 0 to 3 back to 1 to 4. Okay. Okay, originally this should be 0, 0. But for a reason that you will see later on, it's easier for you to see if you move the zeros to 1, and then everything you just plus 1. So the index originally I run from 0 to 3. Now I let it run from 1 to 4. So the original 0 states become the 1 states. Okay? So yesterday we already seen that the 0 states correspond to 1, 0. Or in this case, this is a 4-dimensional matrix. So you just add 2 more zeros. So what will be the 1 state? 0, 1, 0, 0. What will be the 3 state? 0, 0, 0, 1. So because I bump up all the index, so all these things become 1, 2, and so on until the fourth one, it will be 0, 0, 0, 1. Is that okay?
But won't this affect your face? So it is a diamond better for the E to high rate.
Yeah, it will, but we'll fix that later. Okay, so what we did is basically something like this, right? And then this corresponds to 1000, right? If you do the matrix multiplication. So in the end, you will see that uh, the cat correspond to, so this will correspond exactly, JK will correspond exactly to your matrix element. Sorry. Right? If you try, let's say 2, 3. So 2 is 0, 1, 0, 0. 3 is 0, 0, 1, 0. So this will be all 0. This will be right. So the reason why I bump up the index for here for the second step is to show you that um, the cat correspond to your column. Sorry, yeah. Second correspond to your row index, and then the other one correspond to your column index. So this will be making things easier for you to identify. So of course, when you bump up your index, here you need to minus back, right? Do you get what I'm trying to say? If your index everything you plus one, you want to maintain back to the original equation. So if your index here you plus one, then your J and K affecting your phase has to be minus one, right? To maintain the phase to be the same. So that's one way for you to do it. If you don't want to do that, you stick to the original equation. But now you have to fix your index. So 0, 0 actually correspond to the matrix element A11. Let's say 2, 3 correspond to A3, 4. So it is up to you whether or not you want to do the conversion through the index, or you want to rewrite your equation in such a way that it follows more intuitively how the matrix elements work. Is that okay? So let's try to write down this matrix. I will do the first few expansion, then you start to see the pattern. So let's follow the original equation. That will be 1 over 2. So the first one is J and K equals to 0. So it means that, do you have any phase? You don't have any phase, right? So you have 0, 0. How about 0, 1? Do you have any phase? Your k is equal to 0, so you don't have the phase as well. The third one, you also don't have the phase. The fourth one, you also don't have the phase. How about the second one? 1, 0, you also don't have the phase. How about 1, 1? You have the phase, right? It's omega. How about 1, 2? You have omega squared. Okay. How about 1, 3? Sorry. Okay. So do all the summation until the last term. The last term is 3, 3. So what will be your omega? Power 9. Can you simplify it? Probably I should hide this. Power 4 is equals to 1. So power 9 is? Yeah. Is that okay? So what will be your matrix? You know that the first row is just half. So half I move it outside because everything you multiply by half. So the first one, everything is just 1, right? And then you have 1 here, omega, omega squared, omega cube. And then I don't know the rest, but I know the last term is omega. So what will be the rest? This will be 1. Then so this will be 2, 2, right? Sorry, 2, 1. 2, 1 will be omega squared. And then 1, this one, then omega cube. Yeah, omega squared. Is that okay? So that would be your Fourier transform for um small n equals to 2. So your unitary matrix acts on your quantum state from the x representation to the y representation, whereby your y representation basically is given by equation 49. So okay, let me write down x and y first. So so this is X and Y, and your original Fourier transform is given by this. So the very good thing about using this representation is that if you let your QFT X on your X, you can write, um, you can just write everything. Okay, first thing first, for your K, you have this XK. There is a little bit of abuse of notation because the K index is sort of like repeated over here. So by right, I have to use another index, which is like, uh, let's say I use another index P. Okay. So all this summation you can move in front. And what is important is these three things. So the reason why I choose this notation is that it's extremely easy for you to work out. So the J is your cat vector, and then your bra is K, and your bra will form an inner product with P. So this inner product only matches when your K and P are equal, right? If your K and P are not equal, let's say K equals to 1, P equals to 0, then the inner product that you are forming is orthogonal, and that equals to 0. Do you understand this? So by having this kind of notations, you effectively try to match out the ones with orthogonal states that cancel off each other. And this is the delta, which is Kp. It's only equals to 1 when K and P are equal. If K and P are not equal, that's basically 0. So this sort of like cancels off one of the index, which is P. So that's why this whole unitary matrix, in the end, it just gives you Y, which is like something like this. Did I miss something? Yeah. So you get your Y states to be something like this in terms of X. So you also know that your Y states is equals to the sum of J equals to 0 and minus 1. Um, Y, J, J, So if you try to match element wise, then your yj will be equal to sum of k uh, from 0 to n minus 1 e to the power of 2 pi ijk divided by n. Sorry, this should be k. I think there is a little bit of confusion of notation as well. It's fine. Uh, so which is the same as the equation that I give you here. So that's how you go from equation 48 to equation 49. Here I just show you why the unitary matrix of quantum Fourier transform is extremely useful using this notation. But in general, what the Fourier transform does is to transform um, a certain state into another state with this particular rule, equation 49. So if let's say you don't want to understand what is actually happening, you just sort of like take equation 49 as the rule of thumb for now. So let's look at for a single qubit, what will be the Fourier transform? So you try to expand using the equation. So this equation is from equation 48. Single qubit, your n equals to 1, so your capital N will be equals to 2. So that's why you have e pi ijk and then j and k. So you expand this, so you find that your e to the power of pi I is equals to -1. So that will be your Fourier transform for one qubit. So now you try to act on your qubit with the 0 state. And here I show you exactly how you does it by example. Just now I show you in general, if let's say you have a general summation, how it works. So now I show you specifically what are the special cases, because this is easier for you to identify. Like when you see the 0 states, they basically form inner product equals to 1. So that's why you have the 0 states here. But this one, the second term cancels off. The fourth term also cancels off. So you know that the Fourier transform from 0, eventually it will just give you the plus states. And then the Fourier transform for 1, it gives you the minus states. If you want to test things out, just now we already did the quantum Fourier transform for 2 qubits because small n equals to 2. I'm not sure if you want to do this, but if you want to try things out, you can do it for 0, 0, and 0, 1 and see what will be the results. I think for time purposes, we should skip this, but you can do it later if you want to. Okay. So one thing that you need to notice is that Fourier transform is a unitary matrix. So there will be what we call as the inverse Fourier transform as well. So if the Fourier transform transform a quantum set from x to y with this particular equation, the inverse will be transforming from y to x, only with the phase equals to a minus sign. So this you change to x, this you change to y, and then there is a minus sign. So just for you to notice this. And what will be the quantum Fourier transform circuit looks like? It's a very complicated circuit. So there are basically two components. The first one is the Bn. Later on, I will tell you what is Bn. The second one is the permutations, Pn. So you don't necessarily need to perform the permutation. The permutation depends on your machine. Like for IBM, the way they label the qubits are sort of like counterintuitive compared to what we write. So you need to do the permutations to transform the qubits from, okay, so we usually write, if let's say we want to write the states for here, we usually write K0, K1, K2 until Kn. So this is the first qubit, this is the last qubit. But sometimes for the quantum computers that you use, sometimes they label it backward. The K capital N is labeled, it is put with the first qubit, and then the K0 is the last qubit. So if you want to make it consistent in such a way that the computational results match with your calculation results, you have to do the permutation. So this permutation block, it depends on your machine. Sometimes you have to do it, sometimes you don't have to do it. So for this sake, we just put it here. So now what is Bn? Bn will be a series of gates like this. You have your Hadamard on your very first qubit, and then you have all the control rotations for the rest of the qubits. So what is Rn? Rn is basically a unitary rotation given by this particular equation. Don't worry about like all the complicated stuff. I have one example in here. But for now, just remember, roughly speaking, this kind of structure, whereby you have a Hadamard gates and then all the rotation, control rotation gates. I'll give you the slides later if you don't want to copy as well. So what is Pn? Pn, as I said, is a permutation gates. Uh, so the notation is basically a cross connecting between two qubits. So if you see something like this, the first notation here, so it switches from Kn minus 1 to K0. So Kn minus 1 becomes K0, K0 becomes Kn minus 1. So over here, Kn minus 2 becomes K1, K1 becomes Kn minus 2. It just switches the location of the qubits. So a permutation gates for two qubits, you can break it down into three control NOT gates. So this is what we usually implement in quantum computers. Like I said, it depends on the hardware, how they order the qubits. Sometimes you don't need to perform that procedure. So now let's look at one example. This is a 3-qubit quantum Fourier transform. So coming from this particular equation, equation 50, I've already listed out the rotation gates, R2 and R3. Okay. Okay. Let's say you initialize everything. Wait. Okay, I did not. Okay, this is a bit more difficult to go through. So basically, I sort of like break it down into steps. For example, the first step, what will be the get set look like? It will be after you perform Bn, B3 in this case, right? So Bn basically covers all the qubits, and then Bn minus 1 cover one less qubit, and so on and so forth until you reach B1. So the first step basically is B3. Or if you follow the notation here, n minus 1 is p2, then p1, p0. So remember, there's always a Hadamard gate on the first qubit, and then followed by followed by all the control gates. So let's go through step 1 first, after you implement the first B gates. Okay, so you don't know what is your KJ for now. You just know that you want to implement the Hadamard gate. So you don't know what is K0 in this case. You just want to implement Hadamard gates. So this stays true. This actually follows from a result we have yesterday. If your Kj equals to 0, then this is 1. It becomes the plus state. If your Kj is 1, then this will become the minus states. This is a result that we have from yesterday on how Hadamard gate works. So what is minus 1? Minus 1 is basically e pi I, e to the power of pi I. And you can multiply your Kj inside. And for the sake of writing into the binary notation, I divide Kj by 2. Then I need to multiply outside with 2. So Kj divided by 2, it will be Kj times 2 to the power of minus 1. So remember back just now the binary representation, that will be 0.Kj in the binary representation form. Is that okay? So this is the first step where you apply the Hadamard gate on the first qubit. In general, this will be how it works. So now the second thing is the control rotations. When your when K2 is equal to 0, you are not performing your rotations. When your K2 is 1, you are performing the rotation. So here I wrote when your control, like when it is 0, you basically do nothing. When it is 1, you do some rotation. This is how a control rotation works. Okay. So what would be the end state of step 1? So starting from K0, so I'm just looking at K0 because the only transformation for step 1 is on K0. K1 and K2 does not change, right? So I only need to look at K0. I don't need to look at K1 and K2. So let's look at K0. So you perform the Hadamard gates and you get something like this. This is from the previous result, 51. Then you perform the control rotation R3. So you get a phase on the 1 state. You get nothing from the 0 state. Then you perform the control rotation on R2 again. You get nothing from 0 state. You get something for the 1 state. So now you look at this. The reason why I write in this way is because this is exactly your binary representation of decimal places. So this will be 2 decimal places away from the decimal point. This will be 3 decimal places. This will be 2. So then you write in the decimal form. Then you basically have this as your end results. So I will pause for a while if you want to digest this. If you have any question, you can ask. So one thing I can do to test your understanding of this part is to ask you to calculate what is the result of step 2. What will be K1 after step 2? Try to find out what is the K1 state after step 2 by performing the same sequence that I did just now. If you need me to switch to the other slide with the equation, I can do that. Okay, let me write down the equation that you need, and then I show the slide. So I switch to my tablet. You should be able to see this. So what you really need is the rotations based on step 2, and then how the Hadamard gate performs on KJ. Try to find out what is the end result of step 2 and step 3. Rotational matrix means you can think of it as a unitary matrix, but it rotates the quantum states of the Bloch sphere. In this case, think of it as a unitary matrix for now, because I did not really cover what is the Bloch sphere and everything. So think of the rotation matrix as a unitary matrix for now. So again, looking back at your first step, you find that after acting on the Hadamard gate with all the control rotations, it introduces the phases, and the phases can be added up together. In the end, you have 0.k0, k1, k2. But this is not the decimal representation, it's a binary representation. So what would you expect after step 2? There's no effect on k0, right? Because k0 comes from the Hadamard gates. But you still have the effects of R2 and the Hadamard gate from K1. So what would you expect for the final equation of step 2? 1 over square root 2, 0 plus e to the power of 2 pi I. And then what will be your binary representation? 0 point. K1 comes from H, K2 comes from R2. Right? K0 comes from the H, K1 comes from the this rotation, K2 comes from R3. So it's sort of like if you can't really understand the mathematics, one very quick way for you to see this is that the H acting on the qubit by itself introduces the K0 decimal. R3 will introduce K2. R2 will introduce K1, depending on which is your control qubit. So in this case, you will have what decimal? 0 point, K1, K2, right? So what will be step 3? 0 point, K2. Do you get it? Okay. So if you can't perform the mathematics, understand how it works. Essentially, your BN gates here just introduces the decimals into your binary representation. Hadamard introduces the original qubit by itself, and then all the control rotation gates introduces respectively what will be the control qubit, the phase into that.
So what clarification? So R3 only add on K0, right?
R3 acts on K0 and it is controlled by K2.
Oh, so it's not add on K2. So
it doesn't add on K2. K2 does not change. Yeah. So that's why for the BN gates, you can only look at individual qubits. You don't need to write down everything. So this will be your final results. So I stated step 3 just now, but I haven't performed the permutation matrix. Permutation basically rotates. So in this case, your K1, of course, does not change because there's nothing for you to permutate. But K0 will change to K2, and K2 will change to K0. That's why this is the original result for step 3, the first one. Because you do the permutation, that's why it becomes the top one. The second one remains the same, and then the very bottom one is actually the result of step 1 before the permutation. So is this okay so far? Like, do you guys understand how this works? So if let's say I add one more qubit, so what will be the circuit looks like? So let's say I add one more qubit. So the first step, what would it look like? You will have Hadamard over here, and then R4, R3, R2. So R4 will be controlled by the last one, and then you have the second one. So what will be your final state for this particular step for K naught? You basically have 0 plus E2 pi I 0 point K naught, K1, K2, K3, 1. I don't care about what is in front. The more important part is the phase. So understand how the code, how the circuit works. If you can't understand the mathematics, the mathematics is just for you to show that it really works like that. But if you can't, just understand how the circuit roughly looks like and how does it work. Okay. So that will be the first part, which is uh, Fourier transform. Do you guys need a rest? Mhm. Yeah. I suppose we can pause for a bit, maybe 10 minutes before we continue. So The second part, okay. The second part of Shaw's algorithm basically relies on the phase estimation algorithm. And you can think of phase estimation as the reverse steps of the Fourier transform just now. So basically what the phase estimation does is that uh, it tries to identify the phase of some unitary matrix, which is given by equation 54, by having another quantum circuit and perform the transformation. So let's say this is the states that you want to estimate the phase with. So you sort of like couple it with another system, which is initialized at the zero states. And then you try to do some transformation so that the zero states evolves into the final stage, which is phi. And then you measure phi to obtain the phase through the measurements. That's roughly the what it tries to do. And you see something very similar to the Fourier transform just now, whereby in this case, all these things that you have, so this will be your initial states, and then this is the quantum states that you want to estimate the phase with. So the symbol over here, it means that this is not one qubit states, this is n qubits. So this depends on the kind of like quantum, the quantum states that you want to estimate the phase with. So if let's say this is some n qubit quantum states, then this is basically n qubits. So how many qubits that you need on top depends on the precision that you want to measure. The more, of course, is the better. So you can start to see that it is a little bit opposite to the Fourier transform, whereby Fourier transform, you have one Hadamard over here, and then the control rotation is going upwards. Here is the opposite. You have all the Hadamard in front to prepare you into some superposition of states. And then you perform all the rotations at the bottom. Then at the very end, you perform the inverse of quantum Fourier transform to obtain back the phase. So remember just now, when you go from X to Y, basically you introduce a phase. So when you go from Y to X, there is a minus sign over here. It sort of like cancel out the phase and then leaves you with your X. And the X that you measure basically tells you the phase. You see how sorry, now. So let's start with, again, a 3-qubit quantum phase estimation. A very simple example. So let's say you have a unitary matrix that introduces this particular phase. So now we look at what will happen after first step, all the Hadamards. Basically, you have all the plus states, and then you tensor out with your sign. Okay. So step 2 means that you operate all your unitary matrices, and it is actually not that difficult to understand. So let's look at the first unitary, control unitary first. So the third qubit controls the sum unitary on your sign. So the first 2 qubit did nothing. So I focus on the third qubit first. So as mentioned before, if you look at the Fourier transform just now, when it is 0, it does nothing. When it is 1, it introduces a phase. The thing is, the phase that you that unitary matrix introduces. So originally this would be the plus states tensor with the sine. Okay, let me write this down. So originally over here, this will be plus, tensor with plus, tensor with plus. And then, okay, this plus, you need to write them together because there is a control gates involved. So when the third plus states is 0 plus 1 sine. And then you have the plus states, two plus states in front. Originally, it should be like this, but because of the control unitary, when it is 0 states, you introduce nothing to the whole thing, to the whole system. When it is 1, you introduces the phase. Okay? So the phase here, I put the square bracket. Later on, you see why. But this will be the phase that you introduce. And you can see that even though your control unitaries acts on sine, it actually does nothing to sine, right? Both terms contain sine, so you can factor out sine effectively. So when you factor out sine from this particular equation, basically you have plus state, and then you have this thing here as your third qubit, and then the fourth qubit will be sine. Sine actually does not change anything at all. So this will be up to here. Okay. So the effect of this essentially introduces a phase on your third qubit instead of on sine. How about the effect of this? It will introduce a phase to the second qubit instead of sine. This one will also introduce a phase to the first qubit instead of sine. So effectively, in the end, you get something like this. And why there is this 2 square, 2 and omega? Because of this. Look at K. So the second unitary is 2 to the power of 1. The third one is 2 to the power of 2. That's why you have the term 2 squared, 2, and then 2 to the power of 0, which is 1. Okay? So now here's something that you can sort of like assume arbitrarily. Omega equals to 0.k0, k1, k2. The reason why omega cannot be something like this is because when your k0 and k1 is integer, remember that your omega has 2 pi I in front. So any integer interacting with 2 pi I becomes 1. So effectively speaking, the only thing that will remain is basically 0 point all the terms. So in this case, I'm only using 3 qubits. So I only have k0, k1, and k2. If you introduce more qubits, then basically you have more precision. Okay. So we let omega to be 0.k0, k1, and k2. So then you can look at this thing. the first one, the second one, and the third one again. So 2 square omega, because this is in binary representation. So originally this is k naught times 2 to the power minus 1, k1, 2 to the power minus 2, k2, 2 to the power minus 3. So in the end, when you multiply by 2 squared, you will get k naught k1 dot k2. When you multiply by 2, you get k naught dot k1 k2. When you don't multiply anything, you have 0 point k naught k1 k2. So like I said, all the integers, when you multiply with 2 pi I, it just gives you 1. So effectively speaking, only 0 point k2 actually gives you something, the phase. Similarly, over here, you can disregard the k naught and you get 0 point k1, k2. The third one, it will be 0 point k naught, k1, k2. So now this particular form is really familiar with the Fourier transform that we had just now. So that's why I say phase estimation is kind of like the inverse of Fourier transform. So now what you can do is to perform the inverse of Fourier transform, which is done here on your 3 qubits. And then you do the measurement and you would get, through the statistics, you will get your phase. So roughly speaking, that's how phase estimation works. So like I said over here, the integer in front of the binary representation, they are ignored because every integer multiplied with e to the power of 2 pi I j, it will be equals to 1. Sorry, it's just 2 pi I. Oh, okay, I know what I mean. So if j is integer, then basically that equals to 1. So you can disregard the effects of integers. So we have seen that if you have quantum Fourier transform, it transforms your original states into this kind of representation. So now you perform the inverse of Fourier transform, which is your phase estimation. Then you get back the original states and you do the measurement, and then you, through the statistics, you identify the phase. So like I say, you perform measurement, then it will tell you the phase of sign. So what would be the circuit of Shor's algorithm? It's basically your okay, from now on, I will switch through a lot of uh, different windows. So your Shor's algorithm basically is given by this, whereby you initialize your n qubit states to 1. So everything is 1. And then you perform some unitary, control unitary transformation through these states. And hopefully you will get something like this. Remember just now we mentioned that we want to get a to the power x mod n equals to 1. So that when you minus 1 everything and then do the, what is that called? The difference of square, you get 2 factors. So that's effectively what we are trying to do here. So these registers, how many qubits you should use, it depends on the number that you want to factor. If you want to factor 15, how many qubits do you need? 4, right? Essentially, the number of qubit has to cover the number 15. If it doesn't cover 15, you cannot factor it. So how about 21? How many qubits should I use? 5. So okay, I'm not sure what happens. Let's wait for a bit for the HTML to work. Okay, so this is what we call as the second register. This second register needs to cover all the numbers that you like. It needs to be covered by the number. So let's say you want to factor 15. It is the ceiling function of log 2n. So basically, you need to cover 15 throughout the binary representation. So the first register is all the zeros, and this gives you the precision of your phase estimated. If you want to be more precise, you need to have more qubits. Of course, this is through testing. Uh, as long as you have 2 times n of qubits over here, then it should be having enough precision. Okay, so the next thing that you need to know is how do you formulate all these unitaries? So the first one is relatively simple. It's not called modular exponentiation first. Let's look at the first one. And let's study. So this is where I will go to the sorry, let's wait for the module for Shor's algorithm, which I modified from the IBM version. So of course, the first one, you need to run the pip install. Oh no, what did I not install? Uh, should I install this one as well? Is pip install Qiskit, right? Okay. Okay, why is that? Do you remember? I don't. Okay. You need to add this. Sorry, because I was running this through my laptop. So for the one from the GitHub, try to put this in. Uh, pip install Qiskit underscore AR. Can I run now, please? Yep. So the first step for the pip install, you need to add this one. So I did not add this one. Yeah, because they run it on their computer. That's why they did not mention you need this. I modify it to run the simulator. No wonder. So after you do the pip install, you basically can set up everything. So here should be no problem. So for the Qiskit module, basically they try to factor 15 and what is that? Okay, let's go through this one by one. So remember that just now, the first step is to identify a number that is co-prime with 15. So it will be 2, 4, 7, 8, 11, 13, and 14. So you can pick any number, but in this particular example, they use a equals to 2. And they want to factorize 15. So the first step is to identify your first unitary, u2 to the power of 0. So in my slide, I use u2 to the power of 0. In the Qiskit module, they use m2. So you need to understand what m2 does. What m2 does is basically something like this. So when you perform iterations on m2, what you are actually does is to identify 2 times k mod 15. So when the original state is 0, 2 multiplied with 0 is 0. So after the m2, you get 0. And you need to convert into binary representation as well. When your original state is 1 multiplied by 2, you get 2. So the binary representation becomes 0, 0, 1, 0. This is before, this is after. So the third one, 2 multiplied by 2, you get 4. Before is 0, 0, 1, 0. Now it becomes 0, 1, 0, 0. And you perform everything, so on and so forth, until 15. Because you count from 0 to 15. So in total, you have 16 states. Because you have 4 qubits. Do you get what I'm trying to do so far? You have 4 qubits, so the total number that you can represent is from 0 to 15. Convert from 0 to 15 into the binary representation, and then you perform 2k mod 15 to your original state. So the 0 state does nothing. 1 becomes 2, 2 becomes 4, 3 becomes 6, 6 becomes 12, and then 7 becomes 14. 2 times 8 is 16. Mod 15 becomes 1. 2 times 9 is 18. Mod 15 is 3. Perform all these things. Calculate out the binary representation after M2. Now you can see that after M2, the binary representation actually is just a permutation of the binary representation before. So this is where it is a little bit confusing because Qiskit order the qubits differently from what we write. So let's look at the Qiskit codes. So over here, what they did is they tell you what M2 does to your equation. So this is the definition of M2 mod 15. And this will be the circuit. Remember just now I mentioned that the permutation circuit is just breaking down into 3 C nodes. So this is what Qiskit does. You exchange Q3 with Q2, Q1 with Q2, Q0 with Q1. They just break it down into the CNOT gates. But you need to make sure to understand that this way of doing is how Qiskit orders Q3 until Q0. So what they so Qiskit orders like this. This is how Qiskit orders their qubit. Usually we write something like this. So because of this, the way they do the rotation is also different. If you perform the calculation according to this table, the permutation is from Q0 to Q1, Q1 to Q2, Q2 to Q3. But if you look at the order from Qiskit, it's from Q2 to Q3, Q1 to Q2, and then Q0 to Q1. That's the only reason why they operate in the opposite way. But the idea is the same. You perform a series of permutations. So this will be your U2 naught. So now you need to go to the, okay, before you go into that, remember that this is your U2 0, U2 to the power 0, which is this unitary matrix. You need to attach a control qubit onto it, right? Do you understand what I'm trying to say? So this unitary matrix, you perform through the permutations. And because of this permutation, you have what is in the module, the M2 operator. So this M2 operator is your U2 naught, the unitary matrix. But this is just the unitary matrix. You still have a control qubit on top. Your control qubit here controls whether or not you want to apply this. So in reality, after you have the unitary matrix, which is just a permutation matrix, you need to add in a control qubit into it. This is what this particular function does. And if you look at the final results, so Q3, Q4, Q2, Q3, and Q1, Q2, this will be your M2, right? And then you have a control qubit on top, which is Q0. So with this particular circuit, you completed the first step. Okay. So now here's an issue. The issue being that usually for quantum computers, we only operate on 2 qubit gates. Anything beyond 2 qubits is very difficult to implement. So you need to decompose your 3 qubit gates. So like for instance, the first one is a C0 gate, which is what we call as a trophonic gate that takes in the input of Q0 and Q3 and operates on Q4. So this is actually a 3 qubit gate involving Q0, Q3, and Q4. Usually we don't want that. So what we can do is to decompose all these 3 qubit gates into 2 qubit gates by using decompose. When you do that, you should be able to see something like this. So this is what it would be operated when you have this. From 3 qubit gates, you decompose into 2 qubit gates, it becomes this long. Sorry?
Is it like decomposing into 3 qubit gates? Is it like quite
At least for now, when we don't really have a very good qubit and the gates, you sort of have to do that, because the more qubits are involved in a gate set, the more errors you are going to introduce into it. Errors, yeah. So it's kind of like a trade-off, because here the gate set is a lot simpler, but it involves more qubits. Whereas here it involves only 2 qubit gates, but at the same time the circuit becomes very long. So this is not what we call as a shallow circuit. So basically a shallow circuit means you involve a certain number of gates in such a way that the error is still possible, is still within the threshold that you can perform some computations using quantum computers. And this is the reason why Shor's algorithm right now, you cannot really, you don't really do that, because it's too complicated to perform on quantum computers. So this is the decomposed states for this thing. And this is just M2. Now you look at the rest of the list. So you see that if you want a certain accuracy, you need to perform M2. That is your first unitary. The second one is M4. And then the rest is M1. So M1 basically means identity matrix. So you don't need to perform that. So in this particular like a very simple example, what you need to perform is M2 and M4. So for M4, you perform the same thing. You calculate, you basically do this table and then find out what is the permutation, and then execute it on your computer. So the answer is given by here. And this is what we call as the modular exponentiation, because when you come from u to the power of 2 to the power of 0 to the next unitary, is exponentially larger and larger. So 2 to the power 1, the next one is 2 to the power 2, and so on. And a lot of the very complicated computations actually comes from here. So this is where most of your computation lies in. But in this case, again, you are just performing permutations. And after so this is the control gate as before. You have 3 qubits now. Then you decompose it. So this will be the circuit that you will implement on your quantum computer. Remember, I mentioned just now that the original module from Qiskit, actually they try to implement it in, where's that? The real quantum computer. So that's why they need to do the decomposition. Okay. So now, after you find U2 to the power 0 and U2 to the power 1, which is M2 and M4, the rest is M1. So it means that the rest, you basically don't need to perform anything. So remember, just now I also mentioned for 15, n is equals to 4. So you need 4 qubits. And if you want to receive the kind of precision that you want to do, it's recommended for you to have 2n of qubits on top. So which is why from their implementation, you have 8 qubits on top, C0 until C7. T0 basically is the 1 state, and then you perform M2 as your first unitary, M4 as your second unitary, and then that's it. So now one implementation that you can do is to change, what is that? To change this thing. If you look at this particular line, it means that this is for you to achieve some precision that you want to do. So if you look at the circuit by itself, you only involve C0 and C1. Basically, C2 until C7 is not being used. So you can just delete this and the code will still work. So I try this over here. This is my local drive. Yeah. So I deleted C2 until C7 and I just leave with C1 and C0 and C1. And it still works. So then you try to do the simulator. And over here, they will calculate out the measurements. Then if you want to, you can plot the histogram. So over here, I think is the part that I did not mention. So in order for you to identify the phase, basically you need to look at, so you have four sort of like results that you measured. So this will be the phase and this will be so basically this four is the phase. So the thing is, in order for you to identify the smallest number possible for this, so on top is basically your count. At the bottom is your period or cycle. So actually, there is one step that is missing from my slides that I did not manage to have the time to do it, is that you need to find ways to estimate the smallest possible fraction for all four. So over here, when you directly do the division, it's not apparent. So here they directly implemented what we call as the fraction. So this basically helps you to reduce the fraction into the simplest form. When you do that, you would be able to see the fraction is being simplified. So you don't necessarily get the result that you want, but in this case, you get the result, which is 4. That is the cycle for 2. Like we see just now at the very beginning when we do the modular exercise, you see that the cycle is 4. So that would be your correct answer. So finally, you do all the checks. And when your R hits 4, basically you found one of the non-trivial factor 3. So when you find one, the other one, you will automatically find it as well. So roughly speaking, that's the gist of your Shor's algorithm. So yesterday, I tried to run different setups, but unfortunately, I don't have time to finish that. So I will just suggest all these different setups for you to try at home. So one setup is that you have, so for number 15, your A is equals to, the possible A will be 2, 4, 7, 8, 11, 13, 14. So you have this many numbers. So Qiskit did 2 for you. You can try, for example, 7. You can try 11. You can try 13. So what you will need to modify in this case is over here, B becomes Let's say if you want to do it to 7, B becomes 7. Then you need to identify what are the permutations involved. So this has to be changed, which is why I did not do it, because you need to do all the table and stuff. You need to identify all the permutations for, let's say if you want to do 7, that's the first thing you need to modify. Plot out the circuit is fine. Control circuit, this one you have to change, this one you have to change. Then this one is fine, this one is fine. So the next thing that you need to change is identify the U2 to the power of 1. Then you need to do the modulo exponentiation, which is like identify what is the next. So let's say it's 7, it will be M49. So then you need to do the corresponding changes over here and M49 as well. And then plot it out. And also, by the way, you need to identify the kind of precision that you need. So you also need to see what will be the next few iterations that you need to use. So if let's say you have 7 qubits, then you have 7 of these things. So you need to do the M 7 times, unless the rest of it is 1. For A equals to 2, because the rest of it is 1, so you only need to do M2 and M4. If let's say it is 7, you might have M7 as the first, M49 as the second, and then so on and so forth until it reaches to the end. If let's say all these numbers, they are not equals to 1, then you have to perform everything on all the 8 qubits that you set up. So after you do all that, then you run the whole thing and see whether or not when A equals to 7, you can get the results. Try 11, try 13, so you can do all that. I managed to find one paper that did that. If you are interested, you can look at this paper as well. I will post in the chat later. So essentially, they did I think they did 7 and 11. Okay, let's just scroll down. They did 7 and 13. Okay, sorry, they did n equals to, sorry, 8 and probably they did 8. So this will be the circuit. So you see that this is more or less the same thing. So the first one is 8 mod 15, and then you have x squared, and then 8 to the power 4, and so on. So this is what we call as the modular exponentiation. So you just perform all that. So over here, they actually identify what would be the changes that you need to make for your unitary matrix. So if you want to follow this, I think you can. So this will be one way for you to do it. So if you don't want to follow n equals to 15, you want to factorize other numbers, you can also try, for example, n equals to 21. Then you need to change a few things if you want to factorize a different number. So the first one is to identify what would be the possible A's for n, let's say 21. Then you need to identify the coprimes. And then you need to identify what will be your computational basis and the permutations. Then you need to identify, you need to change these, the swap gates and so on. Um, yeah, more or less you need to change quite a lot of things because now your n equals to 21. So you have 5 qubits now. So more or less, these are some of the things that I can suggest you to do at home if let's say you are curious. The code here, they works. You just need to know what to change. So I think that's all from me. Anything you want to ask? If not, I think I can give the floor to Prof. Anaja to say something. Uh, yeah. Prof, if they want to run, they can run.
We think only continue with our focus in the center.
Maybe you come here and see.
No, don't need time for it a bit and do with the things. What time the break?
It's 12, but now it's 11. Yeah.
So I will give you this this research area that we working on it. Yeah.
So
Are you sharing the screen?
Yes, right?
I think Dr. Chong is sharing.
You
Chong, 你要关掉你的 share screen。诶，你关了？我这里还看到你啊。
can share.
哦，关了，关了。I share the entire screen.
Can
Where? Checking.
I share sound, share everything?
Chong，你看一下，现在有 share 这 screen 了。这个你那边，哦，你关了哦。
Now I already share.
I think
This one.
your screen sharing. Let me check.
Just now, you go back to the. Okay, this one.
Yeah, you're okay to go.
Okay, everything all right? Can you hear my sound and then the share screen? Okay, now, okay, I can start now. Okay. Okay. Okay, please check if online is okay. Online okay or not? Okay. I have noisy, yeah. Okay, this section should be brief, maybe 20 minutes on whatever research activity that we have here in UM that we start on the 2023 to do the Center of Excellence in Quantum Information Science. Yeah. So basically, we also like how to be excellent, still thinking towards the excellent. Yeah, but I think we have some people, some good students, and then a lot of the researcher. Actually, it's not so much. Yeah, working on this field, but we start to collaborate with the MyQI. Dr. Chong, I know him because of the MyQI activities, Malaysian Quantum Initiative. Yeah. So we start to talk. Original is from Prof City. Okay? Prof City working with the MyQI group first. Yeah. And then he he also handles Center of Theoretical Computational Physics. I was in that center too. Then he kind of like want to focus on the Center of Theoretical Physics and want to open more for more field. Okay? Quantum information science and tech can be with various researchers from different fields. So he kind of like, okay, hand into me for the coordinate with all researchers in the first phase. Okay, so I will update you what we are doing and then what we want to focus on. Yeah. Yeah, and then what we currently really link with the industry. I think this one is really important for you as you start to form the hardcore with the basic mathematics, physics. It's a very good chance for us to do something different and then make a difference in the Malaysian quantum future, right, Dr. Chong? Yes, because this one is really key to me. You know, like the number of people, we out of number, right? We out of facility, not enough. We still don't have the hardware and software too, right? But software, everyone developing, correct or not? Starting, developing which application, still don't know, like many things can apply. So you got chance to work on the quantum computing, to be different, to be frontier. For me, in my frontier, I will say a very simple term, you do the future work. That's why you can get the impact. Future work. So when I look on my track record, you was like, why become like professor one now, whatever. I just like keep doing whatever I interest and then whatever new things, whatever make me motivate to do more on the modeling and simulation related to the chemistry with different field. I'm not doing a kind of like routine job. There's a routine job, but routine job is like kind of like nothing, is like not so exciting. The same algorithm or the same pattern all the time to different projects like that. I'm more interested in apply new things to my projects like that. So, but that one also very slow. So when I see my track record, I was like, why I come until this stage, right? So basically, we outnumber out of facilities all the time. But what I've been doing is always do the frontier. That means the future works. Currently with this center also as well. No one want to step in the beginning, you know, like too hard. How to do with QC, with chemistry. So I take a challenge because maybe I already own enough. Yeah. Some new researcher is they already start on a certain area. They don't want to change already. It's too many. I am in the state that I want to make a difference, want to make a change, want to make things really impacts. So I open for all things. Yeah. So this is the things that we are interested in. Okay. So you already know that many applications that time in 2023, we still try to convince the VC that we want to have this center or something like that. Yeah. Now no more question already. QC, the whole world, quantum computing, people really fighting towards it, right? Like, yeah, like no clear. At that time, it's like NVIDIA want to do or not in the QC, too huge investment. Is it like really wasted money or something? Now it's like US, China already like fighting to be number one like that. So I was like, see many YouTube or many news. I was like so exciting. Which one gonna win? Yeah. But whatever, let's try to start to learn and then do all more on algorithm. But again, myself now after this workshop, Dr. Chong, you give me inspiration to have our own hardware. I don't know how to get it yet. Okay. Get too excited already. Okay. So we want to get get the hardware too, but I think the future is will be cheaper. But you really need to look for the people who can do the hardware. I have no specific person to link now, but I only know Dr. Yap in the UTM hardware, and then Dr. Samsudin. If you the name of the person that I mentioned, they are key my QI initiative. You can go and look in the website, and then you will see who is really key in Malaysia to do things from the starting. Yeah. So you can link to those people wherever your area is, and then to start the collaboration. I think this is the best way to start to work the people in Malaysia. You also can try to get your knowledge overseas. Everywhere. We really happy that you can bring the technology back to help us. Yeah. I'm not Malaysian, but I very inspired to work in any region communities that I'm in. So I'm like also more to the Thai and then the Malaysian in this region. So I will like contribute a lot in this too, because I have the connection more. So I emphasize on that. Yeah. Okay. So this one is no question already. It's important. Yeah. And then at the beginning, Prof. City mentioned that the two things that is gonna hit first is this area. The whole world also talking about like quantum security first. So quantum security first. And then the second one is quantum computing. And at the beginning, I was like, I only can do quantum computing. I don't know how to do quantum securities. After for a while, Dr. Chong, you believe or not, I start to get training for the IT people and Dr. Yap. Yeah, but on the algorithm, actually that time because Dr. Chong not free, then I have to give a talk on the quantum algorithms. It's for the IT people, for the IT company with Dr. Yap. So that time I realized that actually nobody know very well on how to really do on the quantum securities and then make it realities. And then we start to like see the people talking with Dr. Samsudin on the key distribution, yeah, KQD, and then GM Telecom Malaysia really need to play important role to work with the quantum securities. And then some more, I start to connect with the friend from the Bank Niagara, want to discuss on the quantum computing. And then I just tell you whatever is happened to me, and then you can like intervene whatever you want to do. It's echo enhanced, yeah. So Bank Niagara, I have some friend who want to get discussed and train on the quantum computing. Even though it's like kind of far, but I think it's like gonna hit, I don't know when, but only cyber security now also important, but we don't know how to like move on the quantum computing yet. And then National Securities Data Agency Thailand. This one want to start to do with the workshop first. Workshop, yes.
Did you share?
Share the screen. Where to share the screen already? Okay.
Just now you just share one screen.
The entire screen, right?
Sharing.
Is it on? Now, okay, I don't know what's, yeah, sorry about this, yeah. So now I just, open, just talking about two starting projects that maybe need to focus first on the quantum securities and then quantum computing. Okay. This context actually Prof City thinks that we have capabilities and then people working on it for the quantum computing. I'm doing the material modeling design, something like that. So it could be used the optimization. And then we have two scenery that we want to prepare. The first one is how to preparing Malaysian towards the quantum threat. This slide by Dr. Siti is a high level for the national preparation. So some part I really don't know how the update going on. Okay, but I think this is something that we really have to plan. Yeah. Okay. So cybersecurity. And then we could start working with the Bank Negara on usually the things that we want to, how we develop the collaboration, usually by the workshop, hackathons like that, in order to work together first and see how we move together. So it will be exchange between Thailand again and then Malaysia in order to do the workshop. Yeah, okay. Okay, or this. Okay. Okay, and then we have the my QI. Okay, you see some of this Prof. Thomas. Yeah, you will meet him online this afternoon, and Dr. Samsui here, and then Prof. Siti. Yeah, okay, and then Dr. Yap somewhere. Yes, and then Dr. Raymond from physics. Yeah. Okay. And then scenario 2 on the quantum computing. In this part, we already have the MOU with the Sanadu to do the activities. We start with the Penny Lane. Penny Lane is like another platform similar to Qiskit. If you check online Penny Lane, there is installation and then the learning and trainings. We will have the micro credit course, either for the industry or for the student, maybe early next year, and then you will get the certificate. This is not a free course. It's for the people who want the certificate in order to use it in their CV. Okay, so we will have the course on the quantum machine learning, AI. Okay. And okay, we start to work with the Sanadu since 2023, got a MOU already, start to do the trainings, use Penny Lane, and then next step is more to the access to their quantum computing to use. And then you can see that at the end, when we use their hardware, you have to pay. Whatever you use in the cloud, in the future, even though you develop your own things, your own algorithm, if you don't have hardware, you really have to pay for them. So I think Malaysia really have to focus on certain part on to do some hardware. Okay, but maybe in the next phase. Yeah, our first phase focus on the algorithm learning. Yeah, okay. Okay, this is Marx. Yeah, then we discuss, and then I go Stuttgart in order to see the lab. The lab is a semiconductor lab. In this one is with the another company called the Quantum Billions. They have a branch in Singapore, Australia, German. Okay, so I visit their lab. So that's why I say the best option for us really want to do is not so photonics. Yeah, photonics you can study, but it's kind of like very too expensive for us to do. You can sustain the hardware for superconducting in NV deficiency. The one that Quantum Billions use is using the diamond nitrogen deficiency. So if you really if you really want to do hardware in this area, we really lack of the researcher to do this research. That's why we cannot like really integrate in this series for the hardware. What I mean is currently what we have to do is using there yesterday in the after training, you see the one that we discussed. It's like they have their own software that we install as a simulator in your computers to start with. In order to work, we also have the MOU with this quantum millions. Then after this, you want to integrate with the HPC, the ICC in is the biggest hardware for us in So you will integrate their room temperatures, qubit. You see, like it's a room temperature qubit. It look very small like this, and it will integrate with the hardware in this ICC if we have a gram. Okay, it's not that expensive that we cannot do until like that. But I would love to see that we can utilize, we can learn, and then we can produce a new qubit like that. So hopefully, if anyone really can do on this field, it would be very best for us because we really lack of this area. Okay? No one really have the knowledge on the hardware to do here. Okay. Okay, so okay, we have this. Yeah. Okay, so for us, for my QI, I don't know this one already updated or not. The Malaysia Quantum Statistics Technology Roadmap on 2024. No, not yet, right? So until like this, yeah. So I think this part, MIMOS launching this early this year, right? Okay, MIMOS launching the quantum computing with the SDT Korea this year. And then a series of the lecture. I give one lecture on AI, healthcare, and then many series, I think 2-3 series with the MIMOS. In order to working on the QC technologies, but we still have to move more in order to do for the national agenda to have the quantum computing hardware for our own. Okay, need the MyQI to unite and then push, yeah, and then that's why we have the Asian Quantum Summit. Yeah, Asian Quantum Summit this 16? Is it correct? 10 to 12 December. Hope you can join in the UTM, and then if we have chance, Dr. Yap will say maybe move to the NUS for the visit, right? Yeah, so hope you can join, yeah, and then we have some activities with the NUS, I think, with Dr. Yap, okay? So we have to really clarify what Malaysian really want to focus on the quantum computing for who, okay? First one is, this one is Dr. Siti list, preparation for next gen, all of you, next gen technology workforce. All of you that can stand from day one until now, I think you are the key Malaysian quantum future. Celebrate already. Okay, so yeah, please do continue. Yeah, and then we want to really work on the real world problem, and then many technologies on the healthcare. Whatever you think that it could be key technologies. Yeah. Okay, for my one, I will give 2 projects that is hot for my area. Okay, so you can see how to integrate, and then maybe can think of the new algorithm if you math and physics in order to work with related to our projects. Okay. Okay, so I give you 2 very top our research already. Okay, this one start from the modeling and simulation in the proteins and drugs interaction, and then the gene information. So you know that nowadays you have certain mutation, you can really know which drug is suitable. But currently, no one really doing that. Some is like buy the general drugs for the cancer treatment. For example, hormone drugs. So now from the genes information, you want to optimize all the process in order to do the ether repurpose drug if you have new mutation in the gene sequence, or you want to optimize the food that is suitable for your genes using the quantum computing. So we integrate many information. We call omic data. Sometimes it's from calculation, interaction data. Some is from the real lab information. And then we use the optimization. And then the I think you will talk about optimization. Do we have lecture more or not? So usually in these projects we use like QML related, but sometimes, most of the time, we still doing with the classical. Because we don't want to spend money on the QC platform much, but we already have the generative AI in order to integrate information and then suggestion. The part that is a key part that we need to do is we want to do at once for all the interaction in every mutation, and then we want to use it for the early detection. Okay, these are complicated enough. Many genes, many mutations, don't know what type of the cancer, and then you want to optimize it. Okay, so this is a whole idea that we are working on it. Okay, and then the cancer genes mutate very fast. You really need to calculate and then do tackle the things. Some currently is already advanced until you can reverse back the DNA if you know which one is really excited state DNA that you can trigger back. But we only know certain case, for example, like colon cancer only. Another one, okay, this one is become like the apps or what starting first in order to engage. Okay. And this one actually, the CEO, one of CEO is at the back, Lei, yeah. So you can have to thank him that he been through Deep Tech program all the past year, very intense on Saturday, Sunday, and then we have to work on the like finding the venture in industry. Now is like working with the Hong Kong. Okay, so this is the group as a starting. It's just starting. Okay, so please don't like very focus that is our folly. No, we want to expand because in the initial stage just need to get things done fast. That's why during the workshop they say start with 4-5 for the any company, it will move fun. So we start with that, and then we want to expand. So you guys expand more. You want to make IP algorithm, many things you can use. And then we can work towards this company. We want to make this model for the sustain the talent in Malaysia. We don't have R&D, any company R&D don't have much. We want to do that, and then we want to. The thing is, this company is sustainable. We want to really leverage in a high level. How to do that? Yeah, that one is a hard one. The company definitely sustain, but you want to leverage very big scale one. So we need help from you, all of you, to make it. Yeah, cannot do alone. Okay, thank you for this. Thank you in advance to contribute together. Yeah, okay. Okay. Another one is material modeling. Material model for the energy research. Energy research, rare earth. You heard about it, right? Rare earth elements. Okay. So we start to connect rare earth element. These people hot topic all. Yeah. Okay, 3 topics that we working on, very hot one. I share already. Healthcare one, energy research for this one. Okay. And then the last one is environment. Okay, this one, basically this. I go in brief. Okay, nah? Okay. So basically many type of rare earth material that you can model. And then you have to do the calculation and then in order to understand their properties. And then we have different model type for the catalyst. And then also the UM-PDAC, you know, right? Power energies in front of university is the best place to start with the sustainable energies with the hydrogen green energies. So hydrogen green energy is many things there. And then there's working on different kind of catalysts also. So we have to really model this part. Material modeling more to the electrons optimization, where is a combination of the metal, okay, in order to be the good catalyst or other application. This is material. Okay. For the environment, this one, it will be related to the sensor and then material that you want to use for sensor, and then monitoring the information from the sensor integrated automatically. Okay. So this one we are working with the makerspace. Makerspace, you know, right? Near the KK Mart. It have to be involved with the IoT training on the weekend for the Python. We have we work with the Autobotics. Is the key company on the Python training. It's open for you to be the trainer in order to connect with us on weekend. Okay, you see like IoT on the weekend training with the Autobotic company. Okay, so that company is focused on the training and IoT in order to work with the sensor related to the air pollution, water monitoring, whatever environment. Okay. Farming also have. Okay. So I hope you have some idea that the key research focus that we have so far. Please think of something that we can like really work on it and then move forward on it. And then I think our role is can work on the algorithm IP. And then those could be the things that we can really can contribute. Okay? Okay. So I still learning how to gain more benefit for the researcher. Okay. So far, I can see the benefit towards the company, but I also have to really know how the IP really can gain benefit for the researcher as well. Okay, so hopefully we learn together and then give the strong network for the talent on the quantum computing. Okay, thank you very much. Yeah. Okay, now break. Yeah. Okay. Okay, online we take a break and then come back. What time? 3 o'clock. Okay, thank you.
So back to give the talk.
Recording in progress. So, hi everybody. And maybe if you don't mind, I would like to start with the photo. It's always good to have some memories. I don't know, if some of you is in a situation that you can turn on your camera, so please do so. I will take a screenshot. Thank you very much. A special welcome to Schrödinger's pet.
The moment he turned on the camera, then his state has been determined.
Yeah, I think everyone, if you want, you can open your camera for a while and we can take a group photo together.
Okay, yes.
Conclusion.
Group photo.
Because
It's great to see you all. Cool. Oh, it's really, if you are in a situation that it's not so comfortable, relax, right? And greets to you. And originally I actually planned to come in person, but then
Hello,
something
Dr.
happened at home.
Thomas.
So at the end, I'm from, hi guys, I'm in here.
We are here to support
So
you.
I will take a photo. 3, 2, 1. Thank you very much. Okay, the meeting is being recorded. I think before I begin, I show you the slides. Let me also thank the organizers. It's great, guys, that you are organizing this event. And yes, really, thank you very much. And I also like a lot this kind of mixture of theory and experiment. It's nice that we have, so that now I'm after Dr. Yap, and I think in next week there will be something similar, right? There will be something. So Quek will talk about no one knows what, I think as usual, but he's always great. And the other talk is more into some hardcore simulations. And also apologies to you that today I had a really busy day. I know you were emailing me before to confirm that I will be on time. I am on time. And sorry, I just didn't have time to see properly to my email and reply. Okay, so let me share my slides. Let me tell you if you can see it. It should say quantum reservoir processing, noisy intermediate scale, quantum artificial intelligence. Are you seeing it? Yeah.
Yes.
Yes.
I'm showing it. Fantastic. So yeah, that's my topic, right? So essentially when I was thinking about something relevant, and then you said that you will be having these Qiskit sessions and you're going to make it relevant to devices that we are going to build in near future. Then I thought, okay, that sounds reasonable, right? Let me tell you about this, although some of you have heard parts of it. So this is not my work, right? In a sense that it's a joint project, and really I was kind of dragged into it by Tim Liu many years ago. And it turned out that we probably were one of the first groups that actually look into quantum versions of certain artificial intelligence systems that now really are much more popular. The people who actually did simulations and did all the hard work are Sanjeev Ghosh today at the Chinese University of Hong Kong and Tanjung Krisnanda today at NUS. And I hope to tell you at the end that we recently actually managed to get an experiment on these topics in the group of Yvonne Gao. So just published, I don't know, this year, I forgot which month. So what is it that I would like to tell you is so-called reservoir networks. So this is just a terminology that comes from classical computer science. And in classical computer science, they have something called reservoir computer. And it's essentially a bunch of neurons and a network. And they call this network reservoir. Its special property is that it has random connections. And so it's very unlike the neural networks that you're used to, right? Because we often think about these convolutional neural networks where you will have a layer of neurons connected to another layer of neurons, connected to another layer of neurons, connected to another layer of neurons. It continues like that, and you play around with these connections. You essentially, the learning process, it tries to establish the right connections between these layers of neurons. So that stuff is complicated. It takes millions of dollars to train such devices. So naturally, one looks for something simpler. And also conceptually, it's a complicated system to analyze as well. So here, what these guys essentially proposed on the computer science, classical computers part, is that let's take a network where we do not train anything. So this network, once you fix this random connections, you will never ever change them. What you will change is just only one layer of certain couplings that I will show you later to get the final output. So that's the basic idea of this classical reservoir. It's a fixed network that is not going to be changed, and all of the artificial intelligence business just goes on at a single output layer. And it turns out that this is doing the job. So people have shown that this can recognize letters, recognize cats from dogs, and this typical problems. So what we thought is that, and really there is also a conceptual advantage. This system is really more or less simple, right? So then what we thought that let's look at the quantum version of this and let's see what this can do. And the quantum version of this is having a network again, but of quantum bits. So you have a number of quantum bits. I'll show you the exact model later. And this quantum, and you excite some of them. And this line here means that the excitation can hop so for example, from this qubit, it can go here, then there, or back, and so on, right? It can delocalize over the network. And we're going to shoot into this some classical or quantum input. We will let this input, so essentially there will be some interaction, these are these arrows here, between the input and this number of qubits. This will make this network evolve to some new state that we will measure. And finally, we will get some classical or quantum output. So that's the kind of the bird's view on the whole protocol. So why is this an interesting platform? Is that first, it uses randomly connected qubits, which means, so really what this in practice means is that this models imperfections in preparing those kind of networks. So it can deal with actual physical devices. So that's why I wrote that this is this near-term quantum devices that are relevant here. This can be realized on near-term devices, noisy devices. So it turns out that this operates pretty successfully for a lot of different internal dynamics. So this network here, it has, for example, you could choose the hopping terms, but you could choose some other terms, right? I don't know. Well, I'll show you some examples. So there are a lot of different possibilities, and it looks like it's pretty universal. So as long as you have this structure, it can compute. So again, suitable for hardware implementations. It's a fairly simple device, especially compared to convolutional networks, right? It's conceptually simple. It's computationally inexpensive, but if you really want to simulate it on your classical computer, you have the usual limitation of, say, I don't know, 5, 6, maybe 10 qubits, because then just resources are too expensive. And at the end of the day, what we always look at is that as we will simply, to get this classical or quantum output, we are going to measure only individually these qubits of the circuit. We will never look at the correlated measurements. So that's also important and really brings the simplicity into it. You can do this, right? Just like Dr. Yap showed you, for example, in superconducting qubits, each of them will have this readout resonator, and that's it. That's all you need, right? You don't need to study two of them and look, are the results correlated or not? Turns out this is not necessary. It's enough to look at each one of these nodes individually. Okay, so let me just give you a concrete example what this can do. So let's shoot some quantum state into a network, and let's look at the classical output. A concrete problem could be that I have a quantum system here. Let's say it is light, for example, two modes of light, which here I kind of draw as blue and red, initial quantum state. Then we have this reservoir, which is a bunch of qubits. They can be either in state 0 or in state 1 or some superposition, and they can hop between this different. The excitations can hop between these different qubits, and we pump it initially with some laser just to get some steady state of this system. And the question is this input state entangled or not? That is our question. And we would like to build, or I will show you that it is possible to use this reservoir to answer this question actually remarkably accurately. And in a fairly simple way, especially interestingly, by just doing measurements on individual nodes of this reservoir. So again, this network, they call it reservoir. So the protocol is like this, that initially this reservoir is in some steady state with the laser that is being pumped, because we also model the usual kind of stuff that you have. Of course, this qubits decay. They have finite T1, T2, referring to the previous talk. You have to take that into account, and in our simulations, we take this into account. So to get some equilibrium, we pump this system. It is being pumped. Some excitations decay. Altogether, there is some equilibrium, some steady state. We are going to shoot in the input quantum state that from whose photons can hop into this, for example, quantum dots. When they hop, the system goes out of this steady state in which it was before and goes through some transient evolution. And before, of course, at some point it will equilibrate again. And before this happens, we measure the mean occupation number of each one of these nodes and build a vector out of that occupation numbers. So if your reservoir is composed of 3 qubits, then we will have 3 numbers here: 3/4, 1/4, 0, right? The mean occupation numbers that we find at time tau in some transient, at some transient time. And then at the end of the day, we multiply. So now here's what training does. We will multiply this vector of numbers with arbitrary matrix. So not arbitrary, but with a matrix that matches the dimensions of this output vector from the experiment, and such that at the end we get a two-dimensional vector in such that it is equal to 1, 0 if the state is entangled, and to 0, 1 when the state is not entangled. So I think I have some further details here, so maybe let me just go through this. You will see how it goes. So it turns out that this really can witness entanglement of the input state, but even more, it turns out that it can estimate the amount of entanglement. And then once we found this, then we asked, can it do some other things? And it turns out it can actually estimate any nonlinear function of the input, which is very interesting. And then once you see that, okay, it can do so many things, it probably can also do tomography, and that's also the case. So let me show you this in more detail, right? So let's just ask the question, is the input state entangled? And for this results that I'm going to show you in a moment, we used a reservoir of 4 qubits in our simulations. We chose these couplings between the qubits to be some random numbers from -1 to 1, just generated on the computer. So essentially, the reservoir Hamiltonian is just some random couplings, and each node coupled, I think, to every other node. And now the data that I'm going to show you will be averaged over these different realizations of such Hamiltonians, which again means that this system can, in practice, you don't have to manufacture this reservoir very accurately. Any couplings are fine or any reasonable. So something that I always have in mind here is that apparently, if you have 2 quantum dots, then the coupling between them depends on how far away are they from each other. And in the manufacturing of such wafers with quantum dots, it's not so easy to put them each time at one and the same distance. So what these simulations are showing is that you actually don't need that. It's fine if these distances are a bit different in different realizations. And what we did, the method is as follows. First, you have to, it's an artificial intelligence system, so you have to first train it. So what we do, we take a bunch of certain states from quantum optics, so-called squeeze thermal states, for those of you who are familiar with this, but it's really not so important. The important thing is that we chose it in such a way that is essentially half of them is entangled, half of them is not entangled. And we know it from the beginning. So we choose the states and we know if it's entangled or not. So then we run this whole simulation. So we have the input. Input interacts with the reservoir. At some time, we measure the reservoir. We get the outputs, the mean excitation numbers. And so here there is some details about what is this coupling, but again, this is for undergraduates, so doesn't really matter what are these details. As I said, we measure the mean occupation numbers, which in the model are expressed with some sort of quantum mechanics. But at the end of the day, and this is I think the important part, right? What we do is that we will take this mean occupation numbers that you measure for a given input, and we multiply them with a matrix, and we're going to choose the entries of this matrix such that whenever the state was entangled, the output of this multiplication is a vector 1, 0. And whenever the state was not entangled, the output of this multiplication is the state 0, 1. And then there is a well-known method, so-called rich regression, how by having a number of such input states, in our case, I think it was 100 or 200, I can look it up, 200 input states, how given a number of such input states and many vectors of occupation numbers, you can work out the element of this matrix. So this is the training. This is how you train also other neural networks. I mean, but this, I emphasize again, only this matrix is being trained, right? Only the output layer. So really very, very simple, a linear map in a sense. And then we do the following. So of course the question is, so now it's trained, which means that this matrix W is fixed. After shooting 200 input states, you can determine each and every element of this matrix. Of course, now we want to know if this is actually working. So we want to test this. We want to test this machine with new states that it has not seen before. So we choose another set, actually random squeezed thermal states from the same class that we trained, but different states. And we run it through this device. We again measure the occupation numbers. We apply the matrix W that we learned before. And if the final vector is such that its upper entry is larger than the lower entry, we say that, okay, we predict this state is entangled. Otherwise, it is not entangled. And it turns out this is working with efficiency 96%. So it essentially recognizes almost every state from this class. But a really surprising fact is that you can actually shoot states from the class that you did not train. And it still turns out that this is good. So we just played around with some sort of well-known states that people have in quantum mechanics. And each and every time we see that efficiency is close to 90%. Although, I stress again, these are states that have not been shown to this machine. So it somehow effectively, it really learned the essence. What does it mean to be entangled? Because it's pretty good at predicting this entanglement. And I think also this was probably one of the first cases then at that time when an artificial intelligence system was used to answer some quantum question, because here you have a quantum input and the question is some quantum property of that input. And the final result is yes or no, right? So classical bit value, entangled, not entangled, and it works really well. And then we played around and checked with some more complicated functions. And essentially the way these plots work is that the true value is plotted on the x-axis, the predicted values are on the y-axis. So what you would like to see is that the data is just on the black line, but in practice there is some sort of well, as you see, right, there are a bit of errors, but when you make the reservoir larger and larger, these errors are smaller and smaller. We are predicting pretty accurately. And these are nonlinear functions. And so what we did here, we calculate trace of rho to the power up to the power 5, because any function of a density matrix, you can always expand in this powers of rho. So then that really hints at the fact that it's most likely it is possible to actually do the tomography. So by the way, I think we can take it easy. So I will read what people have written. So is the reason why the system can detect whether or not the input system is entangled, no matter if this is the same type of system as the test system, is because we pass it through a fixed reservoir. No, I think so. It is somewhat remarkable that this is most likely one of the simplest neural networks you can imagine. So because you don't train anything inside. So usually when people discuss neural networks, there will be, maybe I should actually, wait a second, I should open this chat as well. People usually talk about layers of neurons and train, which means fix the weights between one neuron and the other. And here it's really nothing like that, right? You just have randomly connected nodes and you only train the one output layer. So it is a bit surprising that it works so well for states that it has not seen before. Why does it work so well? Usually, so I think I can only give you like hand-waving answer, which is, hey, which by the way is the question I think which computer people do not ask, right? So we're just happy that it works. That's it. This is it. But often sometimes people have this kind of picture that every given problem has some specific features. And if you represent this problem so for example, using vectors that are sufficiently high dimensional, there always is some sort of a simple linear cut through this high dimensional space that corresponds to this, at least to binary problems, to classification problems. Is something entangled or not? Is it a cat or a dog? These classification problems, they have so-called feature spaces. And if you represent it in sufficiently high dimensional way, somehow it looks like the linear maps do the job. That's the usual answer. I think it is hand waving, but this is what you would often hear. When you mention 4 reservoir nodes, do you mean 4 qubits? Yes, exactly. These were 4 qubits. Have you tested with classical reservoir computing to see if they can capture the entanglement? We have not. That's actually a good point. That may also be possible if there are sufficiently many nodes. So no, we have not done that. Very interesting point. Yes, if you want to try the simulation, I'm happy to help. Yes. So the second thing is that when you see that this machine can do so many, can calculate so many functions, it kind of is likely that it can really reconstruct a quantum state. And then from this, you can compute whatever you like. So we also showed that that really is the case. And this is one of the rare cases where I can actually tell you what does it mean, how exactly does this machine learn? What does this learning procedure do? So let me try to walk you through this. So the problem here is to work out an arbitrary density matrix. So now the input to the reservoir is a density, some unknown state rho. This state interacts with the reservoir goes out of the steady state. We measure it in the transient. From this mean values, we try to work out what was that rho. So it turns out that's somehow the story, right? And it turns out, and that's, I think, the elements of quantum mechanics that I'm not sure if all of you know, but it is possible. So the density matrix can always be written as a linear combination of d-squared linearly independent states. So so this is what it is. You can choose those states at random, actually, perfectly fine, because if you choose some number of states at random, it's really unlikely. If you choose d square of them, it's very unlikely that you will find them dependent. They will, usually random stuff is just all over the place. So they will be independent. So at the end of the day, so this is our input, and we let it through the reservoir. We measure this mean values for the mean values of excitations for each and every qubit. This is our vector Ni. We make the training and finally try to work out the state by applying this matrix M on the measured values of those, on the measured vector of the mean values. And here it's parameterized in a bit different way, but doesn't really matter. No, I think I will maybe not go to this in too much detail because this is not enough time. But I would just like to tell you what is the gist of this. So you can argue, especially that I think this is a bit more maybe advanced for undergraduate courses. So you can argue that essentially this whole process of interacting when the state interacts with the reservoir and then is measured is actually linear. And then in this whole reconstruction procedure, we also have a linear map. This is just a matrix applied to a certain vector that is given to what we want to reconstruct. So essentially, because of these linearities, it turns out that the learning here is really solving a certain set of linear equations. The learning is effectively just solving a set of linear equations. And then once you solve it, you have elements of this matrix M out. And because here it's again a linear map, so you can work out this. You can work out the unknown state. So that's roughly, this is how it goes. And now then you can ask, so how large this reservoir has to be to do the tomography? And here there is a very nice clear-cut answer. Because every density matrix in dimension D has d squared minus 1 real parameters. And when we measure these mean values, we get 1 real parameter per qubit, which means that you have to have this d squared minus 1 qubits at least to be able to reconstruct state in dimension D. And really, we make the simulations, and fidelity is some sort of quantity that tells you how well you reconstruct your state. And if your state is a qubit, that's exactly, then D is equal to 2, the number of independent parameters is 3, and that's exactly what happens. So you have the fidelity reaches essentially 1 for 3 nodes. Then for a Q-treat, you need to have 8. And for 2 qubits, you need to have 15. And this is where we really run out of computational power. But it kind of scales properly, right? It would cut somewhere there. You can have some other situations where we shoot to classical input to this reservoir, but look for quantum output. And here, the example that we gave, now we will just walk you through this and spend more time on an experiment. For example, one could imagine as just a laser light to be your input. This is considered a simple classical light. Whereas the output could be, so imagine that you shine this light onto, again, say, quantum dots. You excite some of them, then they decay. And when they decay, they really decay quantum light, single photons. And then you can put the single photons on beam splitters and phase shifters and see if you can get some interesting states out of this device. And then we show that, yes, you can. You can get, I guess I'll skip this. You can get so-called Nun states. They are good for metrology. You can get interesting multipartite states. You can get states that are good for quantum computing, or single photon states simply that are relevant for quantum technologies. And finally, one could think about fully blown quantum computation, where you have some quantum input and quantum output. And that we envisioned as something like this, that you have a reservoir here at the center with this reservoir qubits. And then on the side, we have a number of computational qubits, which are the ones where we want to achieve something like, I don't know, Shor's factoring, some things like this, right? So you can imagine that you interact these guys with the reservoir. So reservoir is like a mediator between these qubits, and you optimize the couplings from these computational qubits to the reservoir. And in this really does the job, right? So you can prove that you can essentially evaluate all of the gates that are required for quantum computing. You can evaluate all single qubit gates with fidelities that have 4 nines. So really good quality, but they are also simple, right? They are just single qubit gates. But also you can also do CNOTs with less good fidelity, but still maybe okay-ish. So I think we also showed in that paper the Grover's algorithm for some 4 qubits or something like that, just to have an example. Exactly right. So here I think you have it for Grover's. But I think maybe let me just spend this last few minutes on this experiment. No problem. On this experiment that was done in Yvonne's lab. So essentially, we really went for this tomography. We wanted to show that one can do tomography of a certain system. And here, this is a cavity. This is the tomography of the cavity field, and what this whole device is called is bosonic circuit QED setup, where you have the cavity mode and a single qubit that you use for readout. And there is some sort of modeling involved in this that I think is not suitable for us today. But the point is that you can essentially, we design like two sorts of protocols here. It turns out you can not only work out what is the state, what is the input state, but also what exactly happens in the meantime. So what was the process? And so essentially this whole experiment proceeds in the following steps. So this Yvonne's lab has a pretty nice control over certain set of input states that they can prepare. And so what we do, and these states, there are sufficiently many of them to really allow you to learn the dynamics that happens to them. I think I have an example here. So essentially what they can do, they can prepare Fock states, which means that there is 0 photons or 1 photon or 2 photons, exactly those numbers in the cavity, up to 6, I think it's, yeah, up to 6. And they can also prepare their superposition of this form, that you have some Fock number, so some fixed number of photons in the cavity, plus another fixed number of photons with the cavity, with the phase. And this phase could be 0 or pi half. So essentially, for example, 0 plus 1 or 0 plus I1, 0 plus 2, 0 plus I2, and so on and so forth. There are many such states, altogether d squared. And if you have so many, and they are really, these guys are good at preparing them. So you can trust this. That's somehow important here, that you want these inputs at this stage when you want to reconstruct the process. You want to make sure that the input states are of good quality, and that's the case. And then we gave a protocol, we gave a procedure, which you prepare this d squared states, you let them go through unknown process. There is some dynamics, but you don't know what it is. Then you perform a specific measurement that I will show you in a second. And you work, and again, right, this is, you build a vector out of the mean values that you obtained in this experiment. And you repeat it for this d squared states. And then essentially, we give a way of reconstructing this dynamics. And then once you know these dynamics, you can prepare any other state that you don't know what it is, right? For example, Schrödinger's pet. And then you because now you know this dynamics, you can work out, again, we gave a rule how to do it precisely. You can now work out what this state was. And right, so essentially that's the experiment. So maybe just one thing is that what do they measure here is so-called parity. So parity tells you if the number of photons in the cavity is even or odd. And it's really, so as you see, it's just a binary quantity, 0, 1. So the trick here is that there is a specific interaction between cavity and the qubit that translates this information, is the number of photons even or odd, into the 0 or 1 of the qubit. So if you measure 0, you know it's even. If you measure 1, you know it's odd. But this translation is noisy. And the really important feature of this experiment is that with our method, we really reconstruct the actual process that happens inside this system, including this noise. So this method takes into account systematic errors in this experiment. So this is like visual comparison, and so here really Schrödinger cats were prepared, or rather Schrödinger kittens. So where alpha, so this is often what people discussed in this field as Schrödinger kittens. It's the alpha coherent state plus or minus alpha coherent states. And this is the quantity that tells you how good is your reconstruction of the process. And it turns out that our results are this light blue color. Somewhat the previous methods are the red color, and there is something better than us, as you see, and this is a fully blown quantum simulation where you really put into your master equation, which is essentially the underlying tool that one uses here, all the parameters of the setup that have been measured. So what is the coupling between, what's the frequency of the qubit, what is the cavity decay of that cavity, and so on and so forth. So, and even these fully blown simulations have certain errors that sometimes we are even better than that. And here there is nothing. We learn this process. This machine is capable of reconstructing this process. So the main point, elimination of systematic errors. I think this is super cool, right? The machine learns the noisy dynamics. And a second, which is also, I guess, practical, is that it is economic in terms of resources. So essentially, we always shoot d² states to this device. So for example, in this highest dimension that has been realized in the lab, d = 6, we were training this machine with 36 states. And essentially 6-dimensional reservoir, which means 2.5 qubits. So log of 6, right? And if people have tried this in the past, of course, we're not the first one to do the tomography using this kind of learning methods, but they were not done on the quantum system. Previously, this learning was done using classical neural networks, and look at the difference, right? So really, in these previous papers, I think this is the one here, they used 700 neurons and 7,000 training states. So there is a considerable gain in resources when you move to quantum mechanics. I kind of expected, because this is, again, a quantum problem. You want to work out density matrix. Okay, so I'm done. Quantum reservoir processor, live long and prosper. Thanks for your patience, and yeah, looking forward to your questions. Maybe I will
Any questions from the participants online? Or
keep this. What software and code used to work on? So it jumps. What software and code used to work on reservoir processing? and NISQ AI. So here we were using actually QTIP. So sorry for those IBM people, right? But so these particular simulations that about which I was talking here were written using QTIP in Python, just as simple as that. And as you see, our limitation is essentially 10, which was hard to get to 10. And this was already runtime has some sort of big station, computing station. It's not a supercomputer, but still not a normal laptop, right? So to get to 8, you cannot do it on a laptop. It was already done using some more sophisticated device. Is it possible to get the slides? Would love to get through the details. Sure, yes. So what do I do? Maybe I just send them to the organizers and then we can take a look. Oh, and I forgot, sorry, I have one more slide, especially to Schrödinger pet guy. So it turns out that, so some of you maybe know that from time to time I like playing with biological systems. And here's a successful attempt of me teaching Schrödinger cat to a cat. So in XAML we have at UM, I mean here in Malaysia, we have lots of cats. I don't know, must be the same on your campuses. And sometimes they come to lectures and we manage to catch this guy at the right spot.
So maybe one last question from me. I just wonder, because just now you mentioned like when you simulate your quantum reservoir computers, you don't really need to keep the interactions perfect. So do you like study how much imperfectness or noises that you can cause to the quantum reservoir computers until at one point it doesn't act like a quantum reservoir?
Yes, I think we did that in this. So if you look into the appendix of this first paper, I think we had it there. And where is the beginning? This one. So for example, here, there's an appendix to this paper, and I think we have this there. But essentially, once we normalized into this -1 and 1, then all the data here is being averaged over, I think, 100 realizations with random weights.
Okay.
After this normalization. But of course, at some point, I think the relevant, somehow the decay is relevant. Yeah, you have to be, I think these couplings have to be maybe 10 times larger or so than your decay. If they are comparable to the decay, everything goes away.
All right, thank you.
Something like that.
If there's no other questions online and physical, I think we can thank the speaker now. So thank you, Prof. Tomek, for giving the wonderful talk.
My pleasure again. Okay, thank you very much. Enjoy your workshop. All the best. All the best to everybody. You had a nice kind of comparison with experiment and theory.
Yeah. So I think with this we ended our first workshop of the week. Yeah. Okay.
All the best. Enjoy the second part. See you around.
Yeah, see you. Thank you, Prof.
Thank you.
Bye.
Take care, everyone.
So for the online guests, I think that's the end of the first workshop. So yeah, see you again next week if you join the next week's workshop as well. Bye.
Oh.